There was a time before atoms, before stars, before light itself. We are going to journey back to the universe's very first moments to see what reality looked like before the first atom existed. By the end of this, you will understand the origin of everything you see and are made of. How did our entire cosmic history emerge from a formless, seething energy? What strange laws governed a reality where time and space were not yet fixed? This is the story of our deepest origins. What does it mean that we are built from the remnants of that primordial fire? We begin our journey at a boundary defined by the absence of something we take for granted, stable matter. To truly grasp the pre-atomic epoch, we must first understand what we mean by before the first atom. An atom, as you might recall, is a complex structure. It has a nucleus of protons and neutrons orbited by a cloud of electrons. But in the universe's first moments, these particles could not form, let alone hold together. The pre-atomic epoch spans from the initial moment of the Big Bang up until the universe cooled enough for neutral hydrogen atoms to finally coalesce. This happened roughly 380,000 years later. Before that boundary, the cosmos was an unimaginably hot and dense sea of raw energy and frenzied particles. It was a seething, opaque plasma, a primordial soup where particles were constantly created from pure energy, only to be annihilated an instant later. There was no structure, no permanence, only a chaotic dance of fundamental ingredients. This definition is our anchor point. It marks the era when the universe was too wild for even a single, stable atom to exist. So let us rewind the cosmic clock back to the very first fraction of a second, to witness the birth of reality itself from that initial state of infinite potential. The very fabric of reality was born in chaos. Within the first 10 million trillionth of a second, the cosmos existed in a state so extreme that our understanding of physics simply stops working. This is the Planck Epoch, a fleeting moment where the entire universe was compressed into a space trillions of times smaller than a single atom. In this inconceivable density, the four fundamental forces that govern our reality, gravity, electromagnetism, and the strong and weak nuclear forces, were fused together as one single, perfect superforce. Picture a reality with no particles, no light, not even stable dimensions of space or time. Instead, the cosmos was a seething quantum foam, a turbulent ocean of spacetime itself, constantly bubbling with fluctuations where tiny wormholes might spontaneously form and vanish. In this realm, the very ideas of cause and effect, of a moment before and a moment after, may have had no meaning. As Stephen Hawking suggested, time itself might have behaved like another dimension of space, a concept that challenges our most basic perceptions. This was the ultimate crucible, a primordial chaos from which the first structures of reality were about to crystallize. The universe was poised on the brink of its first great transformation, a sudden and violent event that would shatter the unity of the superforce and set the stage for everything to come. The perfect symmetry of the primal superforce could not last. As the universe expanded past that first unimaginable moment, it cooled just enough for a fundamental divorce to occur. Gravity, the force that sculpts the cosmos on the largest scales, peeled away from the other three. What remained was a single, powerful electronuclear force. This was the grand Unification Epoch, a fleeting era where the universe was still a seething, featureless fireball, but one now governed by a slightly less unified set of rules. In this intense heat, the very fabric of space was a turbulent sea of energy. Fluctuations were so violent that pairs of particles and their antimatter counterparts, like electrons and positrons, would spontaneously burst into existence from pure energy, only to meet and annihilate each other moments later in a flash of light. It was a continuous, frenzied dance of creation and destruction. The critical event of this epoch was the breaking of that remaining symmetry. Think of it like water cooling. For a moment, superheated water can remain liquid, but at a certain point, it must transform, turning into the distinct phases of liquid and vapor. In a similar cosmic phase transition, the single electronuclear force shattered. This was not a gentle separation but a fundamental shift in the properties of reality itself. The energy released by this event, the energy of a broken symmetry, may have been the very trigger that planted the infinitesimal seeds of structure. Tiny quantum fluctuations, microscopic ripples in the dense energy field, were stretched and frozen into the fabric of space-time. These minuscule imperfections would later, over billions of years, become the gravitational wells that pulled matter together, forming the vast cosmic web of galaxies and galaxy clusters we see today. The stage was now set for an even more dramatic and rapid transformation, one that would stretch the infant universe to an unimaginable size in the blink of an eye. This sudden separation of forces unleashed a hidden energy field that had been trapped within the fabric of space itself. A new and peculiar form of energy, known as the inflaton field, suddenly dominated the entire cosmos. Its effect was more dramatic than any explosion. In a span of time almost too brief to conceive, a mere fraction of a second, the universe underwent a growth spurt of staggering proportions. A region of space originally smaller than a single proton was stretched to a size larger than our entire observable universe today. This was cosmic inflation, a theory proposed by physicist Alan Guth to solve some of the universe's deepest mysteries. Why does the distant cosmos look so similar in every direction we look? It is because all of it was once a single, tiny, connected region that was stretched to immensity, smoothing out any initial irregularities. What we see as the vast, uniform sky was once a minuscule dot, but inflation did more than just smooth everything out. It also took the microscopic quantum jitters from the primordial foam, those tiny fluctuations in energy, and stretched them to cosmic proportions. Think of a perfectly smooth sheet of rubber with microscopic wrinkles on its surface. If you suddenly stretched that sheet to the size of a continent, those tiny wrinkles would become vast, rolling hills and deep valleys. Inflation did exactly that to the fabric of space-time. Those stretched-out wrinkles became the first gravitational blueprints, the subtle variations in density that would, billions of years later, guide the formation of every galaxy, star, and planet. Then, as abruptly as it began, inflation ended. The inflaton field decayed, and in doing so, it released its pent-up energy back into the universe in a colossal event known as reheating. This was not a gentle warming but a violent flood that filled the entire cosmos with a raging, hot plasma of fundamental particles and radiation. The universe was reborn from this inflationary event, no longer a strange, cool vacuum, but a seething, dense furnace, now perfectly prepared for the next great act of creation. The stage was set for the universe to build something solid from this chaotic fire. Out of that violent reheating, a new and more structured era began. For the first microsecond of its existence, the universe entered the Quark Epoch. This was the moment matter itself began to assemble from pure energy. The cosmos was now an unimaginably hot and dense soup, a state physicists call a quark-gluon plasma. In this primordial sea, the fundamental building blocks of everything we know, quarks and their force carriers known as gluons, roamed entirely free. They were not yet trapped inside protons and neutrons. Instead, they zipped through the scorching plasma like individuals in a vast, dense crowd, constantly interacting but never forming lasting bonds. The temperature was so high that the strong nuclear force, which normally acts like an unbreakable glue, was too weak to confine them. We have actually recreated fleeting glimpses of this exotic state of matter in laboratories today. Inside the Large Hadron Collider, by smashing heavy ions together at nearly the speed of light, scientists can produce a tiny, superheated fireball where quarks and gluons break free from their confinement for a mere fraction of a second. These experiments are like time machines, allowing us to peer directly into the universe's first moments. Within this quark-gluon plasma, a relentless drama was unfolding. Particle and antiparticle pairs were constantly flashing into existence from the immense energy, only to collide and annihilate each other back into pure radiation an instant later. It was a perfect, symmetrical dance of creation and destruction, but this symmetry was not quite perfect. For every billion annihilations, a single particle of matter, perhaps one extra quark, managed to survive. This minuscule imbalance, this one in a billion asymmetry, is the sole reason anything substantial exists at all. It is the reason you and I and every star and galaxy are made of matter, and not just a fading sea of light. That tiny surplus of quarks was the raw material for our entire future, and as the universe continued its relentless expansion and cooling, a profound change was imminent. The strong nuclear force was finally about to gain the upper hand, permanently locking these free-roaming quarks into the first stable structures. The universe's relentless expansion finally allowed the strong nuclear force to take command. Around a millionth of a second after the beginning, temperatures plummeted below 1 trillion degrees, a threshold that fundamentally changed the nature of matter itself. This was the start of the Hadron Epoch, the chaotic quark-gluon plasma where individual building blocks roamed free suddenly began to organize. The strong force, which had been too weak to bind them in the earlier inferno, now became the universe's primary glue. Quarks, which had been flying solo, were suddenly and irrevocably snapped together into the first composite particles, known as hadrons. The most important of these were protons and neutrons, the very particles that would one day form the heart of every single atom in the cosmos. For the first time, matter had taken a recognizable, stable form, but this new stability was born in a scene of absolute carnage. The universe remained a seething, violent battleground, packed with these newborn hadrons and their antimatter twins, antiprotons and antineutrons. Matter and antimatter particles collided in a relentless storm, annihilating each other upon contact in flashes of pure energy. This was a war of total extermination. If the universe had been perfectly symmetrical, every single proton would have met an antiproton, and every neutron an antineutron. The entire cosmic experiment would have ended right there, leaving behind nothing but a fading, uniform glow of radiation. But our existence is proof that the symmetry was broken. That 1 in a billion surplus of matter from the Quark Epoch, that tiny, inexplicable bias, now became the most important number in the cosmos. Because of it, for every billion mutual annihilations, a single proton or neutron remained. These survivors, the 1% of 1%, became the entire legacy of matter. They were the raw material for every future structure, the seeds of every galaxy and star. These primordial protons and neutrons were still unimaginably hot, careening through a dense, radiant fog, far too energetic to capture electrons or form stable atoms. Yet, a profound transition was underway. With the formation of these stable particles, the balance of power in the universe began its slow, inevitable shift away from the dominance of pure radiation and toward the reign of matter. With the matter-antimatter war mostly over, a new cast of characters took center stage. the universe, now a full second old, entered the Lepton Epoch. The surviving protons and neutrons were still present, but they were no longer the main event. The cosmos became dominated by a far more numerous and frenetic family of particles known as leptons. The most familiar lepton is the electron, and for a few precious seconds, the universe was a dense, glowing fog of electrons and their antimatter counterparts, positrons. The energy of the cosmos was still so intense that pure light, in the form of high-energy photons, could spontaneously transform into a pair of these particles, an electron and a positron, which would then race through the plasma only to find each other and annihilate back into light a moment later. This continuous, shimmering dance of creation and destruction filled every corner of space. Meanwhile, another, far more elusive type of lepton was making its escape. Neutrinos, ghostly particles that barely interact with anything, had been trapped in the dense plasma, but as the universe expanded and thinned out, they finally broke free. These neutrinos began streaming unimpeded through the cosmos, and they have never stopped. In theory, 1 trillion of these primordial neutrinos from the Lepton epoch are passing through your body every second, a silent, cosmic background radiation far more ancient than the light from the first stars. Then, as the universe cooled past a critical threshold around the 10-second mark, the great electron-positron dance came to a sudden and decisive end. The energy dropped too low for photons to create new pairs. The existing electrons and positrons met in a final, universal wave of mutual annihilation. This event released an absolutely enormous flood of photons, a brilliant flash of energy that would become a fundamental part of the universe's fossil record. Crucially, just as with the protons and neutrons before them, the symmetry was not perfect. For every billion positrons that found an electron to annihilate with, one single electron was left behind. These survivor electrons, a tiny but vital population, now drifted through a cosmos that was finally and irrevocably dominated by matter. They were the future. Each one was destined, hundreds of thousands of years later, to be captured by a primordial atomic nucleus, completing the first true atoms. But before that final act of atomic assembly could occur, the universe had one more crucial piece of construction to complete. The protons and neutrons, which had survived their own annihilation, were about to be forged into the very first atomic cores. With the basic particles now assembled, the universe was ready to begin its first and only act of cosmic alchemy. For a brief, critical window between 3 and 20 minutes after the Big Bang, the entire cosmos transformed into a single, colossal nuclear furnace. This was the era of Big Bang Nucleosynthesis, the forge where the very first atomic nuclei were created. The surviving protons and neutrons, which had endured the earlier matter-antimatter annihilation, were now cool enough to be captured by the strong nuclear force. But they were still moving with incredible energy, zipping through the hot plasma and colliding with tremendous force. The first and most crucial step was the formation of deuterium, a heavy isotope of hydrogen. A proton and a neutron would smash together and stick, forging the first composite atomic core. This was not an easy process, as the intense sea of radiation constantly threatened to blast these fragile pairs apart. But as the universe expanded and cooled further, the deuterium nuclei became stable. They then became the building blocks for the next element. Deuterium nuclei collided with each other, or with additional protons and neutrons, to form helium-4, the most stable light element after hydrogen. For those 17 minutes, the cosmos was a frantic, universal particle collider, fusing the primordial soup into its first complex structures. This process also left behind trace fingerprints of other light elements, most notably a tiny amount of lithium-7. And then it was over, By the 20-minute mark, the universe had expanded and cooled so much that the particles were too far apart and moving too slowly to overcome their mutual electrical repulsion. Nuclear fusion on a universal scale ground to a permanent halt. The final elemental tally was locked in for all time. The cosmos was left composed of about 75% hydrogen and 25% helium by mass, with only the barest whisper of lithium. This prediction from our cosmological models is spectacularly confirmed when we look at the oldest stars in our galaxy, or at pristine clouds of gas in deep space. Their composition matches this primordial recipe exactly. This was the universe's foundational chemistry set, a legacy that would dictate the future of every star. The first generation of stars would have only this hydrogen and helium fuel to burn. Yet for all this progress, the universe was still a formless, seething inferno. These newly forged atomic nuclei were completely naked, their positive electric charge wildly exposed. They swam in a dense, hot sea of free electrons, a plasma so thick and charged that light was utterly trapped. Photons could not travel more than a short distance before being scattered or absorbed by a free electron. The cosmos was an opaque, glowing fog, a brilliant prison for light itself. It would take a monumental change, a great cosmic clearing, for the universe to finally become transparent. For nearly 400,000 years after its explosive birth, the universe remained a brilliant, featureless prison of light. This was the Photon Epoch, a seemingly endless era where matter and radiation were locked in a ferocious stalemate. The atomic nuclei forged in the first few minutes, the hydrogen and helium, were now adrift in a searing ocean of free electrons. This combination created a thick, charged plasma that filled every corner of space. Within this glowing fog, photons of light were utterly trapped. A single photon could not travel more than a tiny distance before it would slam into a free electron, being scattered in a random new direction. Can you picture a room so full of thick smoke that a flashlight beam cannot pierce it? The entire cosmos was like that, only infinitely brighter and hotter. It was a uniform, blinding fireball with no details, no structures, and no way for light to carry information across the void. This constant battering by photons created an immense outward pressure, a radiant force that fought against the inward pull of gravity. Any slight clump of matter that tried to form under its own weight was immediately blasted apart by this intense radiation. The universe was stuck, its expansion and cooling the only processes slowly moving forward. The temperature was the master of this equilibrium, keeping all the atoms ionized, their electrons ripped away and unable to find a permanent home, but the clock was ticking. With every passing millennium, the cosmos grew larger, colder, and quieter, inching toward a threshold that would shatter this opaque prison forever. The cosmic stalemate was finally broken by a simple drop in temperature. As the universe expanded past the 380,000-year mark, its temperature fell below a critical threshold of about 3,000 Kelvin. At this energy, the photons of light, which had been the undisputed masters of the cosmos, suddenly lost their power. They no longer carried enough punch to keep electrons stripped away from their atomic nuclei. For the first time, the positively charged protons and helium nuclei could reach out and capture the negatively charged electrons that swirled around them. This process is called recombination, though that name is a bit of a misnomer. The electrons were not recombining with anything from a previous state. They were forming stable bonds for the very first time. Picture a superheated vapor cooling down. At first, individual water molecules zip around freely, but as the temperature drops, they begin to condense into droplets. In a similar cosmic rain, electrons began condensing out of the searing plasma soup, settling onto atomic nuclei to form the first stable, neutral atoms. This was not a single, instantaneous event, but a gradual transition that unfolded over tens of thousands of years. One by one, then in growing numbers, hydrogen and helium atoms blinked into existence. The fundamental nature of the cosmos was shifting at its most basic level. The free electrons that had acted as a countless army of tiny mirrors, scattering every photon of light, were now being taken prisoner inside atoms. With their captors suddenly removed, the photons were set free. The brilliant, opaque fog that had filled the universe for eons began to dissipate. For the first time in its history, the cosmos was becoming transparent. Light could now travel across vast distances without being interrupted, and in that moment of liberation, the universe released a brilliant flash that would one day be discovered as our most profound cosmic relic. This moment of liberation for light created a cosmic fossil we can still observe today. We call this the last scattering surface. It is not a solid wall or a physical barrier, but a spherical shell in all directions around us, marking the farthest point we can see back in time. Every point in space has its own last scattering surface. From our vantage point, it is the distant, spherical shell from which the very oldest photons began their long, unimpeded journey across the cosmos. Think of it as a cosmic birth certificate imprinted on the sky. When a free electron was finally captured by a nucleus to form that first stable atom, the last photon it scattered was sent flying. That photon, once trapped in the chaotic plasma, was suddenly set free. Trillions upon trillions of these events happened across the universe, each one releasing a photon that began a voyage lasting billions of years. These primordial photons, initially blazing with the heat of a 3,000-degree fireball, were stretched by the universe's relentless expansion. Their wavelengths grew longer and their energy faded as space itself stretched, cooling them down over eons. The brilliant optical light of that initial flash shifted all the way down the electromagnetic spectrum, arriving at our telescopes today as a faint, cold whisper in the microwave range. This is the cosmic microwave background radiation, a nearly uniform glow that fills every cubic centimeter of space. It was discovered entirely by accident in 1965 by two radio astronomers, Arno Penzias and Robert Wilson. They were troubleshooting persistent noise in a giant microwave horn antenna, a static hiss that came from every direction in the sky and would not go away. They had inadvertently stumbled upon the cooled remnant of the universe's fiery birth, the afterglow of creation itself. This cosmic microwave background is our most profound window into the infant cosmos. Its near-perfect uniformity, with temperature variations of just a few millionths of a degree, confirms the universe was once incredibly smooth and homogeneous. Those tiny, faint wrinkles in the temperature map are the amplified quantum seeds from the inflationary epoch, the blueprints for all future structure. By studying this fossil light, we can read the universe's vital signs, learning its age, composition, and ultimate fate. Yet, as this brilliant fog cleared and the universe became transparent to light, it also became dark. With no stars yet born, the cosmos plunged into a profound and lengthy cosmic dark age, a period of utter blackness that would last for millions of years. A profound and utter blackness descended upon the cosmos, with the primordial fireball reduced to a faint microwave whisper and the formation of stable atoms complete. The universe entered its longest and quietest chapter, the cosmic dark ages. For the first time, there was no pervasive light. The cosmos was a vast, expanding sea of darkness, populated only by enormous, drifting clouds of neutral hydrogen and helium gas. No stars pierced the void, no galaxies swirled in the distance. If you could have been there, your eyes would have perceived nothing but an infinite, starless night, a silence so deep it lasted for hundreds of millions of years. Yet within this apparent stillness, an invisible drama was unfolding. Those tiny fluctuations in density, the quantum seeds stretched to cosmic proportions during inflation, were finally beginning to exert their pull. Gravity, the patient architect, was getting to work. Ordinary matter, the hydrogen and helium gas, was still too warm and diffused to easily clump together on its own. But it had an invisible partner, dark matter, a mysterious substance that does not interact with light or ordinary matter except through gravity, was the key. This dark matter had already begun to collapse into a vast, invisible network of filaments and halos, creating a hidden gravitational scaffolding that spanned the cosmos. The neutral gas, feeling the gentle tug of these unseen concentrations of mass, began to slowly, inexorably flow toward them. The universe was no longer a smooth soup, but a simmering pot where the first subtle concentrations of matter were beginning to form. This prolonged period of darkness was not a void of inaction, but a necessary incubation. It was the quiet before the storm of creation, the silent gathering of material required for the universe's next great transformation. The dark canvas was prepared, awaiting the spark that would ignite the first stars and end the long night forever. Dark matter was the hidden architect of our cosmos, working in the shadows while normal matter was trapped in a radiant prison. This mysterious substance, which neither emits nor absorbs light, held a unique advantage in the infant universe. While protons and electrons were locked in a violent dance with radiation, dark matter was aloof, entirely unaffected by the searing plasma. Because it only feels the force of gravity, it could begin its work of cosmic construction much earlier. While normal matter was being blasted apart by intense light pressure, dark matter was quietly, inexorably collapsing under its own weight. It began to pool in the faint gravitational wells that had been etched into the cosmos by inflation, forming vast, invisible structures known as dark matter halos. These halos became the universe's foundational skeleton. Computer simulations that model the growth of cosmic structure reveal a startling truth. If we run the clock forward with only the ordinary matter we can see, gravity simply does not have enough time to build the grand galaxy clusters and vast cosmic web we observe. The universe would be a much more barren and formless place, but when we add the gravitational pull of dark matter into the equations, the simulations spring to life. They accurately reproduce the magnificent filamentary structures, the great walls of galaxies, and the immense voids that define our universe on the largest scales. This invisible scaffolding provided the essential framework. The neutral hydrogen and helium gas that filled the dark ages, now free from the pressure of radiation, began to feel the persistent, gentle tug of these unseen concentrations of mass. Slowly, over millions of years, the primordial gas began to flow toward the gravitational wells carved out by dark matter. This gathering of fuel around the invisible blueprints was the final, crucial step. The universe was poised on the edge of a revolution, with everything in place for a single, transformative event, the ignition of the very first star. The entire cosmic architecture we see today was written in a microscopic code. Every filament of the galactic web, every swirling galaxy, and every solitary star owes its existence to the tiniest of tremors in the newborn universe. These were quantum fluctuations, the fundamental jitters inherent to empty space itself. In the quiet vacuum, pairs of virtual particles spontaneously blink in and out of existence, a testament to the restless energy of the quantum realm. During the explosive growth spurt of inflation, these subatomic ripples were not smoothed away. Instead, they were caught in the stretching fabric of spacetime and magnified to an immense scale. Imagine the surface of a still pond, perfectly smooth except for the tiniest nanometer-sized ripples from a single water molecule. Now, imagine that pond suddenly expanding to the size of an ocean. Those minuscule ripples would become vast, rolling swells. This is precisely what inflation did to the quantum jitters in the inflatoned field. Regions that were ever so slightly more dense were stretched into vast hills of concentrated energy, while less dense regions became sprawling valleys. This pattern, imprinted across the entire cosmos, became the master blueprint for all structure. After inflation ended, gravity began its slow, patient work. Those hills of slightly higher density possessed just a little bit more gravitational pull. Over the ensuing eons, they gently tugged on the dark matter and neutral gas drifting through the dark ages, drawing more and more material into their grasp. The faint shadows of these primordial seeds are still visible to us today, etched into the cosmic microwave background. The subtle temperature variations in that afterglow, differences of just a few millionths of a degree, are direct photographs of those density fluctuations. They are the infant universe's first uneven breath. This is the stunning connection between the smallest and the largest scales of reality. The unpredictable, probabilistic dance of the quantum world was transcribed onto the cosmic sky, determining the location of every future galaxy cluster and the vast, empty voids between them. The fate of the cosmos was set by vibrations smaller than an atom, a hum of potential that would one day orchestrate the birth of stars and worlds. Our existence hinges on a broken symmetry. Every atom in our bodies, every star in the sky, is here only because of a fundamental imbalance in the newborn cosmos, a tiny preference for matter over antimatter. The laws of physics, as we understand them, suggest the Big Bang should have been perfectly fair, creating particles and their antiparticles in absolutely equal numbers. For every quark, an antiquark; for every electron, a positron. These opposing pairs should have met and annihilated in a final, brilliant flash, leaving behind a universe of pure, fading light. That this did not happen is the single most important fact of our cosmic history. Something tipped the scales. This mystery, the genesis of the basic stuff of the universe, is known as baryogenesis. To create the world we see, three specific conditions had to be met in that seething early plasma. The first was a violation of baryon number. In simple terms, a baryon is a heavy particle like a proton or neutron, the core of matter. Our everyday experience suggests the number of these particles is conserved, that you cannot just create or destroy them. But in the extreme conditions of the early universe, this rule had to be broken, allowing for a net production of matter over antimatter. The second condition was a breaking of symmetry itself, specifically what physicists call C and CP symmetry. C symmetry means the laws of physics should be the same if you swapped every particle with its antiparticle. CP symmetry is a bit more subtle. It means the laws should hold if you swap particles for antiparticles and also mirror the entire scene. If these symmetries were perfect, matter and antimatter would behave identically, and any excess of one would be impossible. But they are not perfect. We have observed tiny violations of CP symmetry in particle accelerators, proving that nature does, on a minute level, distinguish between matter and its mirror image. The final ingredient was a departure from thermal equilibrium. The universe had to be caught off guard. If everything was in a perfect, smooth, hot soup, any budding asymmetry would have been immediately wiped out. The cosmos needed a sudden shift, a phase transition like water freezing into ice, to lock in the tiny advantage for matter. One leading idea is that this happened during the electroweak phase transition, when the electromagnetic and weak nuclear forces split apart. This event could have created the necessary out-of-equilibrium conditions, acting like a cosmic filter that slightly favored matter. Other theories point to even earlier times, to grand unified theories where the strong force was still merged with the electroweak. Regardless of the precise mechanism, the result was a statistical miracle. For every 1,000,000,001 particles of matter, there were only 1,000,000,000 particles of antimatter. After the mutual annihilation was complete, that one particle in 1,000,000,000 was left behind. It seems like a negligible amount, a rounding error, but that 1 in 1,000,000,000 surplus is the source of every single thing we see. It is the reason the universe is filled with galaxies and not just a thin, uniform haze of radiation. The quest to understand baryogenesis is more than a technical puzzle for physicists. It is a search for the origin of our own material reality, an explanation for the greatest lottery win in history, the one that allowed anything at all to exist. Before particles could even dream of acquiring mass, the universe was a realm of perfect, unbroken symmetry. Around 1/1,000,000,000th of a second after the beginning, the cosmos was still too hot for the concepts of mass or distinct forces to have any meaning. In this seething cauldron, two of the fundamental forces we know today, the electromagnetic force and the weak nuclear force, were fused into a single, elegant entity, the electroweak force. In this state, particles like electrons were massless, zipping through the plasma at the speed of light, indistinguishable from the force carriers themselves. It was a world governed by a beautiful but ultimately unstable unity. Then the universe cooled past a critical threshold. This triggered the electroweak phase transition, a fundamental shift in the very state of the cosmic vacuum. Think of it like the moment supercooled water finally crystallizes into ice. The liquid and solid states are both made of the same water molecules, but their properties are radically different. In the same way, the universe underwent a phase transition, not of a substance, but of the underlying fabric of reality. The single, unified electroweak force shattered, cleaving into the two distinct forces we recognize. The electromagnetic force carried by the massless photon and the weak nuclear force responsible for certain types of radioactive decay. But what caused this great divorce? The key player was the Higgs field. During this transition, this invisible energy field that permeates all of space suddenly acquired a non-zero value everywhere. Imagine a vast, featureless plane suddenly developing a uniform, gentle slope. This new landscape of the Higgs field immediately began to interact with the particles moving through it. Some particles, like the W and Z bosons that carry the weak force, began to drag against this field as if moving through a cosmic molasses. This resistance is what we experience as mass. Meanwhile, the photon, the carrier of light, remained utterly unaffected, slipping through the Higgs field without any interaction, which is why it forever travels at the ultimate speed limit. This single event, this breaking of symmetry, was a monumental step in defining the rules of reality. It created a universe where most particles have mass, allowing them to slow down, clump together, and eventually form the complex structures we see today. Without this crucial transition, the weak force would have infinite range, altering the nuclear processes that power stars and forge the elements of life. The cosmos was now perfectly prepared for its next great act, the assembly of the very first particles of matter from the chaotic energy of the fireball. Our everyday experience of time shatters completely at the universe's origin. We perceive time as a steady, relentless river flowing from the past into the future, but this is merely an emergent property, a consequence of a much deeper and stranger reality. To understand the pre-atomic universe, we must abandon this familiar river and dive into its turbulent source. In the Planck Epoch, when the cosmos was a seething quantum foam, the very fabric of spacetime was not smooth and continuous. It was a churning, probabilistic froth. In this realm, the idea of a single, well-defined timeline dissolves. Wormholes could spontaneously form and vanish, creating shortcuts or loops where cause and effect could become tangled. Some theories, like loop quantum gravity, suggest that time itself might be granular at this scale, composed of indivisible chunks, much like a movie is made of individual frames. In this view, the smooth flow of time is an illusion that emerges from these fundamental, discrete ticks of the cosmic clock. This quantum nature of spacetime challenges the very idea of a beginning. The initial singularity predicted by classical general relativity, a point of infinite density and temperature, is likely not the final answer. It is a sign that our equations break down. At that extreme, the very question, what happened before the Big Bang, may be as meaningless as asking what is north of the North Pole. There may not have been a before in any sense we can comprehend. The physicist Sean Carroll explains that the arrow of time we experience, the reason we remember the past but not the future, is intimately tied to the universe starting in a state of incredibly low entropy, a condition of supremely high order. This was the ultimate wound-up spring. The entire subsequent history of the cosmos, from the formation of atoms to the burning of stars, is just the long, slow unwinding of that spring, the relentless drive toward higher disorder that gives us a direction to time. To witness the birth of the universe is to peer into a realm where time did not flow but flickered, where the words before and after lose their anchor. This journey to the edge of time reveals that our most fundamental perception of reality is just a shadow cast by a far more bizarre and magnificent truth. The void itself holds a secret power. We often think of empty space as nothing, a true vacuum, but quantum physics reveals a far more restless reality. Even in a region stripped of all particles, space is not truly empty. It seethes with a faint background energy, a consequence of quantum fields that fill the entire cosmos. This is vacuum energy, a fundamental hum of existence that has been a silent architect since the very beginning. Its most spectacular performance was during the epoch of cosmic inflation. The inflatoned field that drove the universe's stupendous growth spurt was a dominant form of this vacuum energy, a temporary but immense pressure embedded in the fabric of space that pushed everything apart at an exponential rate. When inflation ended, that stored energy did not simply vanish. It decayed in a violent cascade, reheating the universe and transforming into the hot, dense soup of quarks and radiation, effectively resetting the cosmic stage for the birth of matter. This raises a profound question for modern cosmology. Is the dark energy we observe today, which is causing the expansion of the universe to accelerate, simply a much weaker version of that same vacuum energy? The leading candidate for dark energy is the cosmological constant, a concept Einstein initially proposed to create a static universe and later called his greatest blunder. It represents a constant, low-level energy density inherent to the vacuum of space itself. The puzzle is one of scale. The vacuum energy that drove inflation was unimaginably powerful. The dark energy acting today is incredibly feeble, yet both appear to be properties of empty space. Why is the energy of the void so different now than it was then? This question remains one of the greatest unsolved mysteries in physics. From the first fleeting moment to the present day, the energy of the vacuum has been a constant, shaping force. It built the cosmic stage during inflation, and now, billions of years later, it is writing the final act of the universe's expansion. proving that nothing is ever truly nothing at all. This initial order of the universe presents a profound puzzle, one that challenges our understanding of reality itself. Think of the cosmic microwave background, that near-perfect fossil glow. Its incredible smoothness means the early universe was in a state of supremely low entropy, a condition of almost unimaginable order. It is as if you walked into a room and found every single air molecule gathered in one perfectly arranged corner, an arrangement so specific and unlikely it defies all odds. This is the universe's original configuration, a wound-up spring of pure potential. But where did this information, this specific state of order, originally come from? This is the information paradox of the cosmos. In the context of black holes, physicists wrestle with whether information swallowed by a singularity is truly lost forever, which would violate quantum mechanics. A similar, even grander, conceptual challenge applies to the Big Bang. The universe seems to have begun with a very specific set of instructions, a pristine initial condition that contained the blueprint for everything to come. How did such a highly informed state simply come to be? One compelling idea is that our entire universe is the result of a random quantum fluctuation. In the restless quantum vacuum of a larger multiverse, or perhaps from a prior state of existence, a tiny bubble of spacetime could have spontaneously fluctuated into being. From that ephemeral seed inflated to cosmic proportions, our entire reality was born. This would mean the total information of our cosmos, all its galaxies and stars, might ultimately balance out to zero when accounting for the positive energy of matter and the negative energy of gravity. Another radical hypothesis comes from the holographic principle, inspired by black hole physics. It suggests that all the information describing a three-dimensional volume of space can be fully encoded on its two-dimensional boundary, like a cosmic DVD where a three-dimensional movie is stored on a flat surface. If this is true, then the entire observable universe in its earliest moments could have had its information written on its outer surface. The smooth, low-entropy state we observe would then be a projection of that fundamental data. The evolution of the cosmos, from that initial simplicity to the staggering complexity of today, would be the process of that encoded information unfolding and processing itself. These are not just abstract philosophical games. They force us to ask what the most fundamental constituents of reality really are. Are they particles and forces, or are they bits of information? The transformation from a smooth, fiery beginning to a structured, galactic present represents a colossal increase in complexity, but perhaps not in total information. The quantum seeds for galaxies were always there, written into the fabric of the cosmos from its first breath. We are left wondering if the universe is, at its heart, a computation, a narrative written in the most basic language of physics, whose first chapter was a single, perfect, and deeply mysterious sentence. The singularity is a wall our equations cannot breach, but our curiosity will not accept it as the final answer. To peer beyond that moment, to ask what came before the Big Bang, we must turn to the most ambitious frameworks in physics, theories that attempt to weave gravity into the quantum tapestry. String theory is one such profound endeavor. It proposes that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating loops of energy. Think of a violin string. Pluck it one way and it plays a specific note which we might call an electron. Pluck it another way and its vibration manifests as a quark. In this view, every particle and force is simply a different harmonic resonance on these fundamental strings. This elegant idea has a stunning implication. The universe may have more than the three spatial dimensions we experience. String theory requires extra dimensions, perhaps 6 or 7 of them. all curled up into a space so infinitesimally small that they are hidden from our view. One of the great puzzles of the early universe is how these dimensions became compactified, settling into their current state and defining the very laws of physics we observe today. This framework allows physicists to construct models of a pre-Big Bang cosmos. One compelling scenario is the pre-Big Bang model in string cosmology. It suggests our expanding universe was preceded by a long period of contraction. Instead of a singularity, there was a grand turning point, a big bounce. In this view, the pre-atomic universe, that seething high-density state, was not the absolute beginning but the dramatic transition between a collapsing previous phase and our own great expansion. The intense heat and density we attribute to the Big Bang's first moments were simply the natural consequence of this cosmic rebound. Other theories go even further, proposing a cyclic model where the universe undergoes an endless sequence of expansions and contractions, each cycle beginning with a big bang and ending in a big crunch, only to be reborn again. These ideas fundamentally reshape our cosmic story. They replace a single, isolated creation event with a potentially eternal narrative. While these theories remain highly speculative and are not yet supported by experimental data, they represent the furthest reach of human thought. They are our boldest attempt to answer the ultimate question of origins, to understand what, if anything, came before the first atom, before the first moment of time as we know it. They suggest that our entire cosmic history might be just one chapter in a much grander and perhaps infinite book. This apparent fine-tuning of the cosmos is more than a curious coincidence. The fundamental constants that govern reality, the strength of gravity, the mass of an electron, the power of the strong nuclear force, all seem perfectly calibrated for a specific outcome. If any one of these numbers were altered by even a minuscule amount, the universe as we know it would not exist. Consider the strong nuclear force, the glue that binds quarks into protons and holds atomic nuclei together. If it were just a few % weaker, it could not overcome the electrical repulsion between positively charged protons. The brief nuclear fusion of the Big Bang would have failed. No helium would have been forged, and the universe would be a forever barren sea of hydrogen, with no heavy elements to build planets or life. Conversely, if the strong force were slightly stronger, it would have bound protons together so efficiently that all the hydrogen in the early universe would have been fused into heavier elements. Without hydrogen, the fuel that powers stars like our Sun would be gone, and the long dark ages would have lasted forever. The cosmological constant, the energy of empty space driving the universe's accelerated expansion, presents an even more extreme example. If this value were significantly larger, the repulsive force would have been so powerful that it would have ripped apart the infant cosmos before the first particles could even form. Galaxies, stars, and planets would never have had a chance to coalesce. This incredible precision is what the anthropic principle attempts to address. It is a philosophical idea that observes the universe must be compatible with the conscious life that observes it. We are here to ask these questions precisely because the cosmic lottery produced a universe with the right rules for our existence. One compelling explanation is the multiverse. In this vast landscape of potential realities, perhaps every possible set of physical constants is realized in some separate universe bubble. We simply find ourselves in one of the rare, hospitable ones where atoms could form and eventually give rise to beings who can look back and wonder at their own origins. The conditions of the pre-atomic epoch, the specific way forces separated and symmetries broke, were the very first and most critical steps in establishing this delicate balance. Our ability to contemplate the nature of atoms and the origin of the cosmos is not separate from the story. It is the final, remarkable consequence of that ancient, precise tuning, written into the laws of physics at the very beginning. We cannot see the pre-atomic era directly, but we can hear its echo in the data. Our knowledge of this invisible epoch comes not from a single photograph, but from a brilliant forensic reconstruction, piecing together clues from massive machines, ancient light, and the very chemistry of the cosmos. At facilities like the Large Hadron Collider, we have built the most powerful time machines on Earth. By smashing atomic nuclei together at nearly the speed of light, we recreate, for a fleeting instant, the trillion-degree temperatures of the Quark Epoch. Within the resulting microscopic fireballs, quarks and gluons break free from their confinement, giving us a direct glimpse of the universe's primordial soup. These experiments confirm that matter behaves exactly as our theories predict under such extreme conditions, validating our models of the first microseconds. The next major clue is written across the entire sky. The cosmic microwave background radiation is more than just a uniform glow. Its subtle temperature variations, mapped with exquisite precision by satellites, are a fossilized imprint of the universe at the moment of recombination. This snapshot, taken when the universe was only 380,000 years old, captures the density ripples that were present at that time. By understanding the physics of how these ripples evolve, we can run the cosmic film in reverse. We can trace these patterns backward through the Dark Ages, through the era of nucleosynthesis, and right up to the inflationary seeds that planted them. This backward extrapolation allows us to confidently infer the conditions that prevailed long before the first atom formed. The third pillar of evidence is cosmic chemistry itself. The universal abundance of light elements is a powerful testament to Big Bang nucleosynthesis. When we look at the oldest stars or pristine clouds of gas in deep space, we find their composition is roughly 75% hydrogen and 25% helium by mass, with a tiny, precise trace of lithium. This ratio is a perfect match for the predictions of nuclear physics operating in a hot, expanding universe during its first 20 minutes. It is a relic abundance, a chemical fingerprint that could only have been forged in the universal furnace of the Big Bang. The future promises an even clearer view. The next generation of observatories, particularly gravitational wave detectors, aim to listen for the faintest tremors from the inflationary epoch itself. These ripples in space-time, generated when the universe was a fraction of a second old, could carry direct information about the energy scales of the grand unification of forces. Each of these methods, from particle colliders to ancient light to future gravitational astronomy, forms an independent line of evidence. They converge on the same breathtaking story, a narrative of a universe born in chaos, structured by inflation, and forged in a fireball, all before the first stable atom ever came to be. Deep within the dark cosmic clouds, a profound transformation was silently taking shape. The invisible scaffolding of dark matter had done its work, pulling vast reservoirs of primordial hydrogen and helium gas into its gravitational embrace. Inside these dense, cold pockets, the gas finally began to collapse under its own weight. From this simple, pristine fuel, the very first stars were born. Astronomers call them population 3 stars, and they were unlike any sun we see today. These titans were composed solely of hydrogen and helium, the only elements the universe had forged. Without heavier elements to help them cool and fragment, they grew to colossal sizes, some hundreds of times more massive than our own sun. They burned at ferocious temperatures, shining with a brilliant, harsh, blue-white light that had not been seen since the primordial fireball faded. Their lives were spectacularly short. A massive star burns through its nuclear fuel in a cosmic blink, and these first giants lived for only a few million years before exploding in cataclysmic supernova. But in their brief, brilliant lives, they irrevocably changed the cosmos. Their intense ultraviolet radiation began to flood the surrounding space, striking the vast neutral hydrogen atoms that filled the universe. This immense energy was enough to blast the electrons right off those atoms, tearing them apart and turning the neutral gas back into a charged, ionized plasma. This great upheaval is known as cosmic reionization. It was not a single instant, but a rolling dawn that swept across the cosmos. One by one, then in growing clusters, bubbles of ionized gas appeared around these first stellar nurseries. These bubbles expanded and merged over hundreds of millions of years, eventually filling the entire universe with a diffuse, ionized medium. The long cosmic dark ages were over, replaced by a universe once again transparent to ultraviolet light. While the first stars lit the way, the dark matter halos continued their patient construction, pulling together multiple star-forming regions and vast clouds of gas. These collections became the first protogalaxies, the humble seeds from which majestic spiral and elliptical galaxies would eventually grow. This period, from roughly 100 to 500 million years after the Big Bang, was a true cosmic renaissance. It was the moment the dark, simple universe of drifting gas awakened into a structured, luminous cosmos of stars and islands of light. Today, we are witnessing this epochal transition ourselves. The James Webb Space Telescope, with its infrared eyes, is looking back in time, peering through the dust of ages to capture the faint glow of these very first galaxies. Every distant smudge of light it discovers is a direct glimpse into this final, magnificent act of cosmic dawn, the ultimate culmination of processes set in motion long before the first atom ever existed. The emergence of everything from a state of apparent nothingness forces us to question the very meaning of existence. We are compelled to confront the most fundamental riddle of all, a question posed by philosophers like Gottfried Wilhelm Leibniz centuries ago. Why is there something rather than nothing? The pre-atomic universe suggests that our intuitive idea of nothing, an empty, black void, is completely inadequate. True nothingness would be the absence of space, time, energy, and the very laws of physics. It would not be a blank stage waiting for a performance, but the absence of the stage, the play, and the concept of a performance altogether. So, was the singularity an absolute beginning from this kind of nothing? Or is our question flawed because we are trying to apply the logic of our universe to a realm where that logic does not apply? Perhaps there was no before because time itself was born in that event. The laws of physics that allowed for the Big Bang, the quantum fluctuations, and the inflationary field, they seem to be a pre-existing eternal framework. They are the rules of the game that must exist for the game to be played at all. This blurs the line between physics and metaphysics, between what we can measure and the deeper nature of being. Our consciousness, which allows us to ponder these mysteries, is itself a product of this cosmic evolution. We are the universe awakening to contemplate its own origins, a loop of self-awareness that began when the first quantum tremors were stretched across the cosmos. The journey from a formless potential to the intricate structure of an atom is the ultimate story of emergence, where complexity and beauty arise from the simplest, most austere beginnings. Our voyage to the beginning reveals a cosmos built from chaos, a universe that transformed itself from a single point of infinite potential into a structured reality governed by elegant laws. We have traveled from that unified singularity to the dawn of atomic matter, tracing a story written in the language of physics and permanently etched into the cosmic microwave background. We witnessed how microscopic quantum fluctuations were stretched to cosmic proportions, becoming the gravitational seeds for every galaxy. We saw how the breaking of fundamental symmetries defined the very forces of nature, giving particles mass and making complex chemistry possible. Most crucially, we discovered how a 1 in a billion asymmetry between matter and antimatter made our entire material existence possible. The era before the first atom was not an empty void but a dynamic, evolving crucible that set every parameter for the universe we now call home. As Carl Sagan so poetically reminded us, the cosmos is within us. We are made of star stuff, but we must look even deeper. Before the stars, we were made of the primordial ingredients forged in the universe's first few minutes. Before that, we were the energy of the inflattened field, and before even that, we were the quantum tremors in the first fleeting moment of space-time. This knowledge should inspire more than just intellectual curiosity. It should instill a profound sense of wonder and a deep connection to the epic history of the cosmos. Every atom in your body carries the legacy of that primordial fire. Let this understanding reshape your place in the universe. If this journey to the edge of time has sparked your curiosity, subscribe for more deep dives into the great mysteries of space and share your own thoughts on this incredible epoch in the comments.